Okay, so I would like to introduce Rishabh Sarma, who's going to talk to us about relating the smallest missing part with other partition statistics. Rishabh, if you want to take it away.
Thank you, Michael. I am glad to speak to everyone at this symposium today, and I thank the organizers for this opportunity. And I am currently joining you guys from my home in India. So the title of my talk today, as Michael said, it is relating the smallest missing part with other partition statistics. And this is a work done by me with my friends in Florida, Aritram and Avi. And this was a work that we started at the end of fall last year and completed sometime in January this year. Right, so what I want to talk about in this presentation is about the minimal excludant or max of a partition function, which is the smallest missing part in an integer partition. And it was defined by Andrews and Newman in 2019. And we try to explore relations of this particular new statistic with other partition statistics, well-known partition statistics, and other partition theoretic objects as well. So I begin with a picture of Professor George Andrews, who has been at the center of every major breakthrough in the field of partitions and Q-series. So a partition pi of a positive integer m, it is a non-increasing sequence of positive integers such that the sum gives you n. And these summands are called the parts of the partition, and let Pn be the number of such unrestricted partitions of n. Here is an example. There are 7 partitions of the number 5, and as you can see, if you look at a partition, the parts are in non-increasing order. I'll be using this notation a lot. The third notation, which is Q infinity, it is an infinite sum. It is the infinite product. It is the product of 1 minus q to the power k from 1 to infinity. I'll be using Q infinity the most. Any standard talk in partitions always begins with always has these famous congruences of Ramanujan. So if Ramanujan gave these congruences, proved these congruences in 1919. So if Pn is the number of partitions of n, then the number of partitions of the number 5n plus 4 is divisible by 5. Similarly, the number of partitions of 7n plus 5 is divisible by 7, and 11n plus 6 is divisible by 11. And although Ramanujan did give a proof of these congruences in his paper back in 1919, a combinatorial explanation of these congruences were always missing until Freeman-Dyson came into the picture. And in 1944, he gave the rank and crank statistics. And let me define the rank, the Dyson's rank of a partition. It is the largest part minus the number of parts. So as you can see, there are 5 partitions of the number 4. And for example, if I take this partition 2 plus 1 plus 1, then the largest part here is 2, and there are 3 parts. So 2 minus 3 gives you minus 1, which is the rank of this particular partition of 4. And if we look closely, then there is 1 partition of 4 in each residue class modulo 5. If we reduce the rank modulo 5, then the remainders are 0, 1, 2, 3, and 4. And as we can see, there is 1 partition of 4 in each of these residue classes. And this indeed is not a coincidence. This is the famous Dyson's rank conjecture. So Dyson states that if NTN denotes the number of partitions of n with rank congruent to R mod T, then the rank statistic divides the partitions of the number 5n plus 4 into 5 equinumerous classes. As you can see, if we take T to be 5, and then R ranges from 0 to 4. That is exactly what happens here. As you can see, these are 5 equal classes. That is why the partitions of the number 5n plus 4 is divisible by 5. The same thing happens for partitions of the number 7n plus 5 as well. There are 7 equinumerous classes here, equinumerous sets here. That is why the partitions of the number 7n plus 5 is divisible by 7. This was conjectured by Dyson in 1944 and proved by Atkin and Swinnerton Dyer in 1953. And a nice thing to note here is that the rank function, the rank statistic, does not give a explanation, combinatorial explanation of the mod 11 congruence of Ramanujan. It fails in case of the mod in case when p is 11. That is to say, the rank statistic does not divide the partitions of the number 11n plus 6 into 11 equinumerous classes. But here lies the genius of Dyson. Although he cannot explain, he is not able to provide an explanation for the mod 11 congruence of Ramanujan, he does give a prediction that there will be a different arithmetical coefficient, a different arithmetical statistic which he calls to be the crank, which will successfully explain the mod 11 congruence of Ramanujan. And what amazes me more is this is a work that was done by Dyson while he was an undergrad in Cambridge University, and this work got published in the undergraduate journal of Cambridge University called Eureka. This was given by Dyson in 1944, and nearly 44 years later, George Andrews and Frank Garvin came up with the definition of the crank in 1988, and they defined crank as the largest part if there are no ones in the partition, and otherwise it is the number of parts larger than the number of ones minus the number of ones. Complicated as this definition looks, and I have indeed seen the proof, the generating functions and the proofs are indeed difficult, indeed complicated, but they do give a very successful explanation of not only the mod 11 congruence of Ramanujan, but all the 3 congruences postulated by Ramanujan simultaneously. That is to say, the crank statistic M divides the number of partitions of 5n plus 4 into 5 equal classes, equinumerous sets. Similarly, the partitions of 7n plus 5 into 5 equal classes and 11n plus 6 into 11 equal classes. And hence, this gives a very nice explanation of why the 3 Ramanujan congruences hold. This is the last statistic that I'm going to be talking about before moving on to the next. This is the SPT function of George Andrews. Once again, Andrews is in the picture, and this came up in the Rayleigh Journal back in 2008. And in this revolutionary paper, what Andrews defines is the SPT of n, which is the total number of appearances of the smallest part in each integer partition of n. And the amazing fact here is that the congruence properties similar to the partition function are also satisfied by this SPT function of Andrews, except for the last partition congruence, where, as you can see, instead of the 11, we have a mod 13 congruence. I gave a background of these statistics because my plan now is to relate the MEX or the new MEX statistic with these statistics. That's what we have done in our work. So I would like to begin with the definition of the MEX function. So in 2019, the paper of Andrews and Newman that came up in the Annals of Combinatorics, they defined the MEX of an integer partition phi to be the least positive integer that is not a part of phi. As you can see in this particular partition, the smallest part that is missing is 2, hence the MEX is 2. In an upcoming paper in 2020, what they did was they defined an extended function of this MEX function. It is defined MEX of capital A small a of phi is defined as the smallest integer greater than or equal to small a and congruent to small a modulo capital A that is not a part of that partition. Further, they define PAA to be the number of partitions pi of n where the MEX is congruent to small a modulo twice of capital A, and the overlined P or P bar to be the number of partitions where the max is congruent to capital A plus small a modulo twice of capital A. One can't help but wonder how is such a definition motivated? What is the motivation behind such a definition? And indeed, it turns out that what they got in their paper, what they have in their paper is that this relates to the rank and the crank statistics. The max, when defined with a congruence condition in such a way, we have that P11 equals the number of partitions of n with crank greater than or equal to 0. Similarly, the P33 relates to the rank, and P21 relates with a restricted partition. This is where we began our work. We tried to generalize these results. We tried to see what happens when we consider different cases of the small a and capital A. So I'm going to describe them here. Let me consider the Q series that has these PAA and P bar A as its coefficients. In that case, here is our first result. We find the generating functions of these two extended max functions P and overline P. Here is what they look like. And here is a sketch of the proof for the first generating function. I'd like to reiterate that PA of n is the number of partitions of n where max is congruent to small a modulo twice of capital A. So what happens is the max, which is not a part of the partition, it looks like 2na plus small a. So that is the part that is missing. So we do not include that part here. And since it is the smallest missing part, all the parts before that have to be included in the partition. So that is exactly what happens in the numerator. In the next line, what I do is I divide and multiply by Q infinity, which, if you remember, is this particular product without the m not equal to this factor. It is the product, infinite product, m from 1 to infinity, 1 minus q to the power m. I'm multiplying that on the numerator and the denominator. And when I do that, the numerator gets cancelled, and the only term that remains is this max term, 1 minus q to the power 2n capital A. And on simplifying further, we get here is the exponent of q has these even ends and the odd ends, and on further simplification, it leads us to the simplified form of the generating function for the non-overlap max extended function. The generating function for the overline PAA, overline extended max function, is very similar. And this helps us, this particular generating function is at the heart of all our results. This helps us to find the relation of the max with the rank. So it turns out that P bar of 3j plus 1, where the capital A is 3 here, it equals the number of partitions of n with rank greater than or equal to j being a non-negative integer. So the proof of that starts with the generating function of the number of partitions of n with rank n. This was given by Dyson in his paper in 1944. And to find the number of partitions of n with rank greater than or equal to j, all that we need to do is we need to take a summation here, a summation for rank greater than j. That means the summation runs from j to infinity. And that is indeed a very easy sum over here, a very elementary calculation over here. And it leads us to this generating function. And as you can see, this is very similar to the generating function of the max that we had before, for the overline max that we had before. The capital A and the small a are coefficients of n into n plus 1 and n plus 1 over here. That gives us a lot of leverage, since we have those exponents of a in different places, the small a and the capital A in different places. So we get a lot of leverage there, and we can align this particular exponent of q as per our requirement. And what we get is a relation of the rank with the max function, extended max function. The result for the crank is very similar. We have a generating function for the number of partitions of n with crank m. And similarly, as just like how we got it for the rank, we take the summation from j to infinity to find the number of partitions of n with crank greater than or equal to j. And that sum gives us a relation of the extended max function with the crank. It turns out that the three results of Andrews and Newman in their paper are corollaries of these two theorems B and C that we have here. As you can see, in case of the crank, the extended max function that is related to it, the A here, capital A here is 1, and for the rank, the capital A here is 3, which is exactly similar to Andrews's and Newman's result. Also, the overline max and the non-overline max, when added, they add up to the total number of partitions of n, and they are disjoint sets, which is why these corollaries B1 and C1 are also follow obviously from theorems B and C. The last relation that I have is the relation of the max with the SPT function, and for that we need the Atkin-Garvan rank and crank movements. It is nothing but an infinite sum of the rank function, the total number of partitions of n with rank m. It is an infinite sum with a weight factor at the front. The kth Atkin rank moment is defined in this way, and the crank moment is defined the following way. And Andrews has a characterization for this particular SPT function in terms of the second Atkin-Garvan rank and crank moments. As you can see, SPT of n is half of the second crank moment minus the second rank moment. And this gives us a very nice characterization of the rank and the crank moments in terms of our extended max function along with a coefficient at the front. Similarly, the SPT function is, as we have seen before, it is half of the second crank moment minus the second rank moment. That is exactly what we have here, and this is indeed a finite sum. This is how the proof of that follows. We have a generating function from the second rank moment thanks to Atkin and Garvan. And on slight manipulation and simplification, once again, we can align our generating function with the generating function of the extended max function that we have obtained before. And as a result, we find that the second rank moment is a finite sum of the maxes, overline maxes with a coefficient at the front. The result for the crank and the SPT follow similarly. At the end of my talk, all that I would like to say is that the story does not end here. Along with these well-known partition statistics, there are other partition theoretic objects as well with which we can relate the max function, extended max function, and it turns out that there are several congruence conditions that you can attach and find relations with the differences of max of different varieties, as we can see here. Here we consider an even moduli, congruence modulo an even number, and here congruence modulo an odd number. And the difference of maxes also depend on the divisor and the residues as well. And the proof of these follow from the Jacobi triple product identity that I will not include here. And as you can see, these are some specific relations of the difference of maxes with some congruences into some specific congruences into parts, some specific parts here. And one can't help but notice that there is a general pattern over here. In the capital A and the small a, there is a general pattern over here. And what we have noticed is that as the capital A and the small a increase in these, keep on increasing in these shifted extended max functions, the congruence condition here becomes even more complicated. That is why we stopped at 3. We could not go any further, but we do believe that there is a general pattern here that needs to be explored more, studied more. And that is the first question that we have, is if there is a general pattern of these identities of the shifted partition nature, like this result, theorem G. A second question that we pose is that, is there any other linear combination of these maxes that lead us to restricted partitions? For example, we can see that it turns out that when these two maxes are added, we get the generating function for that is the same as the Euler's pentagonal number theorem, which is indeed in turn the generating function for the unrestricted partitions of n. And maybe it could be that if we add or subtract or take any other linear combination of other max function, extended max functions, we could land in a subset of Pn. Thirdly, all the work that has been done on these extended max function, the original max function, or any other varieties of max functions since the work of Andrews and Newman, people have always looked for bijective and combinatorial proofs, but there aren't any in the literature as of now. So we too are looking for bijective. We could also look for bijective proofs or combinatorial proofs of these rank and rank theorems or any other restricted partition theorems that I stated previously. I would like to end my talk here with a picture of my co-authors back in Florida. Thank you so much.
Thank you very much, Rishabh. We have time for some quick questions. Are there any questions in the audience? If so, just raise your hand in the little raise hand function. Call out. Doesn't look like there are any questions, Rishabh, but we are also running a bit low on time in some sense. So I'll thank you again, and I think everyone will join me in thanking Rishabh.
Thank you so much.
Thanks very much for a great talk.